Okay, while people are still trickling in, welcome everybody to our first distinguished lecture series seminar in the new year. I also greet anyone joining via Zoom. As you know, the DLS is our main seminar series here at the Max Planck Institute for the Science of Light, introducing to you the thought leaders in the science of light worldwide. So it's a particular pleasure today to introduce Professor Yiwen Chu, from ETH. Let me briefly say something about her CV. She did her undergraduate studies at MIT, and then she moved a few hundred meters, I guess, across to Harvard, where she started her PhD in the group of Mikhail Lukin, trying to couple light to NV centers in diamond and looking at the quantum optics of this very interesting system. After graduating with her PhD in 2014, she then moved on to explore another area of quantum physics, which is the field of circuit quantum electrodynamics or superconducting qubits coupled to microwave resonators, for which she moved to the lab of Rob Schoelkopf at Yale, the inventor of circuit quantum electrodynamics. And there, also in a collaboration with Peter Rakic, whom some of you may know, she managed to couple superconducting qubits to massive mechanical resonators. And that's where I got to know her work. So then in 2019, she was appointed an assistant professor at ETH, where she remains since then, and her work has been internationally recognized. So in 2020, she got the Sackler International Prize in Physics for her achievements. And in ETH, she is now currently leading the Hybrid Quantum Systems group. So we are really looking forward to your talk. We already enjoyed the discussions we had today, and take it away.
All right. Thank you so much, Florian, for the very nice introduction. And thank you so much to all of you for having me here. I'm looking forward to being able to tell you a bit about the work that we've been doing at ETH Zurich. So my group there is called the Hybrid Quantum Systems Group. And basically what we focus on is looking at massive mechanical objects in the quantum regime. Okay, so to just explain sort of a bit what that means, let me bring you back to perhaps your very first quantum physics class, where we all learned, right, that there's this quintessential system, the mass on a spring, that acts as not only a classical harmonic oscillator, but also has this nice quantum mechanical description, right, in terms of these quantized energy levels and excitations. In this case, would be called phonons, because this is a massive object that's mechanically moving around. But I think ever since then, none of us have actually seen, a block of some mass moving attached to a spring, right, behaving quantum mechanically like this, right? And of course, people have come up with even more fantastical situations involving even more complex, massive objects doing quantum mechanical things, which also no one has observed, perhaps for the best. And so, we of course have many ideas as to why it is so difficult to see these, sort of quintessential quantum systems actually behaving quantum mechanically, and that's because, a block of some material attached to a spring is pretty complicated. So is a cat, and yes, many degrees of freedom, many component parts. Most importantly, many ways of interacting with the environment, which all leads to, for example, decoherence. And that makes it very hard to then observe their quantum mechanical behavior in a coherent way. Okay, and this might seem like an obvious statement, but I would say, that this whole enterprise that many of us are involved in, building quantum technologies, is kind of asking this question of how complex of a system can we build, right, that still behaves quantum mechanically in a way that we can control and measure and observe, right? So it's sort of a fundamentally interesting question, but also has some very practical applications. Okay, so, in lieu of torturing actual cats, as physicists, we came up with some systems where we can maybe think about, doing an analogous experiment to Schrödinger's original thought experiment by looking at other types of systems where people have made things that could potentially, be called analogous to Schrödinger's cats. So these are so-called Schrödinger cat states. And I'm giving here a sort of a overview of literature that has called certain quantum states by this name. So one example is you can take electromagnetic modes, so light, and put them into, say, superpositions of two, distinct coherent states. So these coherent states are sort of classical analogs of in the quantum harmonic oscillator. And if you take, let's say, two coherent states with opposite phase and large enough amplitude, and you put them in a superposition, people have called those Schrödinger cat states. Okay. Similarly, you can do this with, let's say, trapped ions, where you take the motion of the trapped ions, put them into coherent states, and put them in a quantum superposition, in this case perhaps even entangled with some internal state of your atom. People have also called GHZ states Schrödinger cat states. So these are, for example, large spin systems where you have superposition of all the spins pointing up and all the spins pointing down. Maybe slightly more closely analogous to an actual cat. People have even taken molecules that are made up of thousands of atoms, put them in atom interferometers, and sort of made a wave function that can be thought of as a superposition of being in different locations. Okay. So these are just a few examples, and one can ask the question of how macroscopic are these things? And it turns out, sort of colloquially macroscopic, we kind of have a sense of what that means, but defining that in a rigorous way is difficult, right? What do we mean? Do we mean the mass, the degrees of freedom, the size, the extent of the wave function? There are many different ways that you can talk about that, but let's just take one naive sort of figure of merit, which is just the mass of the system. Okay, and I've taken some of the examples from the previous slide and a few others and roughly put them in, where the mass would be, right, for these different systems. And you can see that even, these atom interferometers, the mass is on the order of about 10 to the minus 20 grams. The internet tells me that a cat is about a kilogram. Although it can be up to 18 kilograms. But either way, there is a large gap, right, between 10 to the minus 20 and 10 to the 3 grams. And so partly what we set out to do is to explore this mass regime in between. And to do that, we are looking at solid-state mechanical objects, right, which is really taking the collective motion of many, many atoms in a solid-state system and trying to see if we can look at their motion in the quantum regime. Now, these solid-state mechanical systems can take on many different shapes and sizes. They can be, for example, these periodic structures called phononic crystals that confine sound, or vibrating drum heads or membranes. And also, they can just be sound waves inside a material, right? They can either be acoustic waves traveling through the bulk of a material, in which case they're called bulk acoustic waves, or on the surface, so surface acoustic waves, maybe like an earthquake, for example. Yeah, and then the idea is that we can use these objects to maybe explore this region in here. Now, I should say that these objects are interesting, of course, for sort of exploring this fundamental question, right, of how macroscopic or massive an object can be and behave quantum mechanically. But also, if we can get them to behave quantum mechanically, that can also be useful, right? And people have come up with different ways of maybe using them. One of them, of course, is as circuit elements in perhaps a quantum processor. And the idea here is that there are several unique aspects of a mechanical system as opposed to, let's say, a electrical circuit, let's say. So people have thought about putting these in, for example, quantum computers made out of superconducting circuits because the speed of sound, for one thing, is much slower than the speed of light. And that means that at the same frequency, you can make much more compact resonators, right? Because your wavelength is much shorter, right? So one can think that, of course, maybe has some technological advantages. Also, it means that you can deal with things like crosstalk much better because the modes are more well confined. And people have also shown that, in fact, these mechanical resonators, at least in the classical regime, can live much longer, can store information for much longer than electrical microwave circuits. Okay, so that's one idea. Of course, going back to some of the original applications of mechanical resonators and optomechanics, of course, they were used as very sensitive detectors or sensors. And of course, the most sort of famous example would be LIGO. So this is one of the mirrors of LIGO, which is in fact about a kilogram. So this is a very massive mechanical object. Right, and one can of course think about how getting to the quantum regime can help improve, let's say, the sensitivity of different mechanical sensors. For example, just simply by getting rid of thermal noise, let's say. And then finally, another sort of unique, let's say, characteristic of a mechanical system is that they talk to everything, pretty much, right? Everything from gravitational waves to across the electromagnetic spectrum to, for example, defects or spin qubits and things like that inside these solid-state materials. So one can think of them as very useful interfaces between different quantum systems for linking them together. Okay. So I'll come back to some of these different applications throughout my talk. But first, let me sort of narrow down what I'll talk about. So today, I'll focus on a particular type of these solid-state mechanical resonators. These are the bulk acoustic wave resonators. You can think of them as I mentioned before, just sort of sound waves traveling through the bulk of a material. And if you shape that material properly, just like you can sort of confine light in a Fabry-Pro cavity, right? You can do the same thing if you take the bulk material, you have two surfaces that act as very good mirrors for sound, and you shape them properly, you can confine sound in the equivalent of an acoustic Fabry-Pro cavity. So very simply, these are the systems that we're going to work with. Now, in the lab, we don't have little, quantum hammers that we can go in and hit them and generate acoustic waves. Most of our tools in the lab are electromagnetic in nature. And so what I will talk about are two ways to talk to sound with light. One of them will be using microwave frequency light, let's say, or circuits, so including, for example, superconducting qubits and other nonlinear elements. And the other will be using perhaps light that you are all more familiar with, so infrared light and optical Fabry-Pro cavities to talk to this acoustic Fabry-Pro cavity. Okay, so again, the mechanical resonators we'll talk about here are actually called H-bars, conveniently. We didn't make up this name. This is a name that it was already being used in classical technologies. It's called a high overtone bulk acoustic wave resonator. That just means that there are many the standing wave has many wavelengths that fit within this Fabry-Pro cavity, like most of the optical cavities that probably you work with. Okay, so let's first start with the electromechanics side of things. And so the devices that we work with are so-called circuit quantum acoustodynamics devices, or circuit Q80. Of course, we borrowed that name from circuit quantum electrodynamics, circuit QED. And they essentially are composed of mechanical resonators coupled to a nonlinear superconducting element, usually a superconducting qubit. And here I'm showing some pictures of different examples of how these things look like. So you can see that these different types of mechanical resonators have been used in these circuit QAD systems. Once again, in this talk, we will focus on these bulk acoustic wave resonators. Okay, so let me start by showing you just what our device looks like to give you an idea of that. So basically, our device has sort of two parts. Okay, so if you look at the top part here, what we have is this Fabry-Pro resonator for sound that I described earlier. Okay, it's basically a piece of sapphire, and the two surfaces of this piece of sapphire confine this sound within this material. One sort of additional feature we have here is actually this curved surface. Just like in an optical Fabry-Pro cavity, you need one curved mirror, right, for the mode to be stable. Same thing in acoustic cavities. And in addition, this curved surface is actually made out of aluminum nitride, which is a piezoelectric material. Okay, the reason it has to be piezoelectric is because of the second part of our device, which is our microwave circuit. Okay, and that in our case, is a transmon superconducting qubit. For the purposes of this talk, all you need to know about what a transmon is that it's a LC resonator, a capacitor, connected to a inductor, but in this case, a nonlinear inductor. Okay, so what you see here, this dark gray shape here, these two patches on these two sides are your capacitor plates. In the middle, this X here represents a Josephson junction, which is a nonlinear inductor. Okay, so this thing is going to act as an anharmonic oscillator, right? Because now we have a nonlinear inductor, and we can treat that as a qubit. Okay, so but this particular qubit has this feature that it has a little antenna that sticks out. So you should all imagine, right, this is just a capacitor. So the field, the electric field is sort of going like this from one side to the other, right? And as it does that, it sort of goes through this piezoelectric material. And of course, the piezoelectric material can convert mechanical energy into electromagnetic energy. And that's what then transduces the field of this electrical circuit into these acoustic waves. All right? So in real life, our device looks like this, which is a little microscope image, maybe to give you some sense of scale. Here's another picture. We're just looking up through this stack here. You see this white shape is the aluminum of the qubit. All these colorful rings comes from just the interference between all these curved surfaces that we have between the layers. Okay? So we take this thing, and we put the whole thing inside a microwave cavity, just an aluminum superconducting box, essentially. So here you see half of this box and the little chip in the middle. We have a little connector here where we can send in microwaves, and we're going to use all the tools that people have developed in circuit QED for controlling and measuring our quantum circuit, our qubit, and through it, we are going to control and measure our mechanical resonator. Okay, and we take this whole thing and we put it at the bottom of a dilution refrigerator to cool it down to millikelvin temperatures. And that's because I haven't mentioned this yet, but both our transmon qubit and our mechanical modes are going to operate at gigahertz frequencies. And at millikelvin temperatures, these modes should be in the quantum ground state. Right? That's a good place to start if you want to look at quantum mechanics of these systems. Okay. All right, so now let me describe in a bit more detail the physics of this system. So again, I've sort of redrawn this in a sort of schematic way. Again, we have our nonlinear LC resonator. Our C is our capacitor, these two capacitor pads here. Again, this X is our nonlinear inductor. Okay, and then what we do is we put our acoustic resonator, in particular this piezoelectric material in here, and as I mentioned before, it interacts through the electric field. So to be a bit more quantitative, we can write down sort of interaction energy between these two modes mediated by the piezoelectric tensor of this aluminum nitride material. It basically depends on the strain and the electric field of the acoustic mode and our circuit, respectively. Okay, and we can then rewrite this in sort of a quantum mechanical language, right? If we just quantize our electromagnetic and mechanical modes. So what I've done here is I'm just treating my qubit as a two-level system, right? So these are the Pauli operators. For that, we have our harmonic oscillator operators for our mechanical mode, which I'm going to just treat as a harmonic oscillator. And they're coupled with some coupling strength, G0. And as I mentioned before, they're sort of both in the gigahertz frequency regime, so very close in frequency, and so we sort of simplify into this Jaynes-Cummings type of interaction here. And we can write down an expression actually for the coupling strength, which again depends on the overlap between these modes and then some material parameters, like for example, of course, the piezoelectric tensor of the material. Okay, so now that I've written it like this, I hope it looks more familiar to many of you. This is exactly analogous to cavity and circuit QED. Okay, we have a two-level system coupled to a harmonic oscillator mode. That's it. Okay, so then if that's something you are familiar with, the next slide might be a bit of a review. But the idea is that what we can now do, this Jaynes-Cummings Hamiltonian, of course, allows us to directly exchange energy between these two systems if we, say, put them on resonance. Right, so you can, for example, excite your qubit. So this is a qubit. You can put one quantum inside. You put it on resonance with your mechanical resonator, and it can swap its single quantum of energy over into your mechanical mode. And now what you've done is you've created a state of a single mechanical excitation, a single phonon in your mechanical resonator. Okay, sorry, and this works well if you start in the quantum ground state and you're in the strong coupling regime where this G naught, the coupling strength, is much faster than your dissipation. Okay, so in this James-Cummings Hamiltonian, actually there's another regime you can operate in. You can operate in the so-called dispersive regime, which is also going to be useful for us. So let me quickly go over how that works. So if you detune these two systems by much larger than their coupling strength, what you will get is an effective dispersive Hamiltonian, turns out, which looks like this. And in this dispersive regime, the interaction can be described as the following. If you look at this Hamiltonian, basically what it says is that the frequency of your qubit, so the stuff in front of this sigma z here, is going to depend on the number of excitations in your mechanical resonator, right? This A dagger A here. So it's the number of phonons, essentially. And every time you add a phonon, your qubit frequency is going to shift by this dispersive shift chi, which is given here by this, according to the system parameters that you have. So in addition, if this dispersive shift is larger, again, than sort of the line width of both of your systems, then what you can see is the following. Basically, it tells you that you can spectroscopically resolve using the qubit frequency how many excitations you have in your mechanical mode. Right? So if you have no excitations, your qubit is here. When you take a spectrum of your qubit, and then if you shift it, if you put one phonon in, it'll shift by chi. If you put two phonons in, it'll shift by another chi. And so just by looking at your qubit frequency, you can tell how many phonons you have. Okay? And so we try to look at this in the lab, and indeed that's what happens. So what we're doing here is essentially, first we're using what I showed in the previous slide, this part, to put phonons successively into our mechanical resonator. So this is the curve we see in our qubit spectrum when we don't do anything to our phonons. This is when we put in one phonon, two phonons, three phonons, and you see that the dominant peak in the spectrum shifts over by this sort of even spacing, which is exactly the dispersive shift chi. You see that also, during this process, of course, there's decay, decoherence, and so you get some leakage into the lower number of Fock states. Okay? And so, okay, this shows us that we can sort of count the number of phonons in our system, but this is not the full story of the quantum state that we have prepared, right? This is just sort of the diagonal matrix elements in your density matrix. What we'd like to do is to do full quantum tomography on our quantum system. And so to do that, actually, we're going to continue making use of this dispersive interaction. And with this dispersive interaction, we can do something called Wigner tomography. Okay, and this is, we're going to measure something called the Wigner function, which is a function in phase space that contains all the information about our quantum state. So for those of you who are not familiar, let me go through step by step how we do this, actually. What we're going to do is we're going to measure something called the parity, which is the sum of all the population in the even number of Fock states minus the sum of the population of all the odd number of Fock states. Okay, and we can do that because, as I said, we can sort of count how many phonons that we have, right? Okay, so now I'm going to make an example using the Fock state 1. Okay, so if we do this, 1 is a odd number, so we should be blue, and we're going to put that in the middle of our phase space. Okay, so this is just the two axes are here are, position momentum, or the real imaginary part of a complex amplitude alpha. What we can also do is, in between making the state and measuring the parity, we can displace our state. That just means we apply a classical drive, or we drive a harmonic oscillator with some complex amplitude alpha. And then at the end, we measure the parity again. Okay, and it turns out that this displaced parity measurement is proportional to the sort of formal definition, the Wigner function. So we do that for a bunch of different alphas. We plot a bunch of points in phase space, and if we do that enough times, what we'll get is this sort of pattern phase space, like a fingerprint of our of our harmonic oscillator state. So this is ideally what you would get for one excitation in a harmonic oscillator. This is what we get when we measure our single phonon state in the lab. So you see that it reproduces some of the important features. Particularly, we see this blue part in the middle. So negativity in your Wigner function is a distinctly quantum signature. It only happens for non-classical states. You see that the contrast is reduced, again, because we have imperfections in our operations, also decoherence in our system. Okay, so this was some work that we did. It came out in 2022, done by my first 3 PhD students that started with me. Okay, so then we went on to look at some more interesting quantum states, perhaps. So now coming back to the story of Schrödinger's cat. So we want to see if we can try and make a Schrödinger cat state of our mechanical resonator. Okay, so the way we're going to do that is the following. So I'm going to walk you through a protocol that we actually copied from cavity QED from many years ago. This was, a protocol that Serge Haroche used to make cat states in a microwave cavity, and we adapted it to our system. Okay, so this is sort of the idea. What we're going to do is we're going to start out in the following initial state. Okay, so we'll start out with our mechanical resonator, our harmonic oscillator in a coherent state. That we can do by just driving it with some classical microwave pulse. And our qubit in this superposition of G and E. So this is like the eigenstates of the sigma x operator, right? Now let's take our James Cummings Hamiltonian, and we're going to say, okay, let's pretend that alpha is, large and real. Okay, it works also if you don't assume that, but you just want alpha to be large. Doesn't necessarily have to be real, but in this case, it's easy then to rewrite your James Cummings Hamiltonian in the following way. Right now, it's sort of just you can pull out A and A dagger as this alpha, and then your qubit operator just becomes sigma x. So now your Hamiltonian is proportional to sigma x, which means that sort of to 0th order in this small parameter here, right? I said alpha is very large. This is sort of the width of your Poisson distribution for your coherent state over the mean, and that gets much smaller than 1 if the mean is large, right? So if alpha is large. To 0th order in this small parameter, this is actually then your initial state is actually an eigenstate of this Hamiltonian, right? So it just gets a phase. That's boring. But it turns out to 1st order in this small parameter, this is what your state does. Okay, so it looks a bit complicated, but don't worry, I'll explain it. So essentially what happens is that your qubit state and your harmonic oscillator state both pick up a phase. In the qubit case, it picks up a phase in the superposition between your G and E states, and it's a phase that evolves in time, like this. But it depends on your initial state, right? And then also depending on your initial state of your qubit, your mechanical oscillator picks up a phase in this complex amplitude. Okay, so maybe it's easier to see this in a pictorial way. If I look at the Bloch sphere of my qubit, right, my initial states are plus and minus. These are states on the equator of your Bloch sphere. And then depending on which one it is, they both actually start to sort of rotate along the equator, and they sort of converge over here. It's just like the plus y state or something like that at some point. And as this happens, depending on the state of your qubit, let's say this blob represents my coherent states for the harmonic oscillator for our mechanical state. Depending on the state of the qubit, they start to rotate around the origin of phase space or around the circle, right? And they separate from each other. Okay, so if that is, yeah. Well, okay, so right, so I'm showing everything, of course, in the rotating frame of the mechanical mode, right? So this is now, does that make sense? So now, I mean, the rotating frame, I guess, is not oscillating, right? It's just some complex amplitude in phase space.
No, it doesn't make sense because now you're using a classical electric field.
That's right.
And you have, let's say, with a sigma plus, you have clockwise rotation. With a sigma minus, you have anti-clockwise rotation.
Okay. Yeah. Oh, you mean of this initial state?
Unless you are doing phase sensitive measure, you are doing homodynamic
So I'm not talking about the measurement at all for now. Okay, I'll show you how. Well, we're going to do Wigner tomography, which I had explained in the previous slide, right? But we're going to do Wigner tomography in the rotating frame of the mechanical resonator, right? So all of the drives that we apply, and the drives that we also apply in our Wigner tomography, right, is resonant, is somehow, with respect to the rotating frame that we choose to talk about our mechanical mode in. Right? And in that frame, right, your Wigner function is not rotating. It's sort of a stable picture. Okay, so maybe let me show you what we get in the end. Okay, so again, right, but okay, that's a good point I did not mention, right? Where all of these Wigner functions I'm showing, all these pictures are, we're looking at the phase space of this harmonic oscillator in its rotating frame. Otherwise, everything would rotate. So let me then also show you some simulations that we did of what actually happens. So we're going to start in 3 different initial states, right? The 2 that I mentioned, and then just the excited state of our qubit, which is a superposition of the 2. Okay, so if we start this, let me maybe do it here. What happens is what I sort of described, right? So if I trace out the qubit and just look at the Wigner function of our mechanical states, right? You see these 2 blobs that separate from each other, and at some time, if I stop this interaction at the right time, you see that in the case where we start out in the excited state of the qubit, you get the superposition of these 2 blobs, and you get these interference fringes in the middle. That is a sign that we have a coherent superposition of these 2 sort of coherent states, right? You see that they're not quite coherent states anymore; they're kind of elongated, and that's due to the higher order terms that I didn't talk about in the previous slide. Okay, and this state approximates then a Schrödinger cat state, right? It's this superposition of these 2 distinct areas in phase space. Okay. All right. So now, we can watch that again, or we can look at the experimental data. Okay. So the way that we measure this state again is using Wigner tomography. Okay. So when we do that, right, initially we have just this blob, which is our coherent state. We let it evolve for some time, and we see indeed that what we get, now this blob is separated into 2 components, but they're well enough separated in phase space and still coherent enough that you can see these interference fringes in the middle. Okay, and it sort of matches pretty well with our simulations. And if you keep going, they sort of converge on the other side of phase space again. Okay. So let's take a step back then and summarize what we see here. Okay, so first I didn't show this, I realized before. So these are the parameters of just our basic parameters of our device, the frequencies, the lifetimes of and coherence times of our qubit mode, our phonon mode, and the coupling. So you see that we're well, okay, it's not so easy to see here, but if you calculated the decay rates, you would see we're quite far in the strong coupling regime here. Okay, so now let's look at this state of our mechanical resonator. Yes? You mean the phonon T2 or the qubit T2?
The phonon one.
Yeah, so for our phonon...
seem to be somewhat comparable to your T1. So are you in a comfortable kind of
right.
coherent regime?
So our qubit T2s indeed are usually close to T1, not twice T1 as it could be. And this is quite commonly seen in superconducting qubits. There's usually some additional dephasing mechanism. Our phonon T1 is a bit closer to T2 is closer to twice T1. In this case, not quite either. We have measured other phonon modes where it's almost exactly twice T1. So we don't see a lot of additional dephasing in our phonon modes, at least not as much as in our qubits. Yeah. Any other questions before I move on? Okay. So let's examine this cat. Okay. So we can talk about, for example, the effective mass of the mode that this cat lives in, let's say, and that's essentially just the mass of this cylinder of sapphire that these mechanical oscillations live in. Right? It's basically saying what are all the atoms that are involved in this oscillation, in this collective motion, and that's about 10 to the 17 atoms, right? And their effective mass is about 16 micrograms. Okay. You can also ask the question, okay, well, how separated are the 2 components of the superposition? Well, in in phase space, you can see that, right? They're sort of separated by some amount. In phase space, which if you square sort of the distance between these, it tells you about the number of phonons that are involved in this cat state, right? So how many phonons that is. But you can also ask, like, physically, right, how separated are the atoms in the superposition? Like, if you zoomed in on this thing, right, in principle, this cat state is like, if you took a snapshot at the right time, it would be like the atoms are a superposition of vibrating up or down. Okay, you can ask, what is the separation for a particular atom? And that is 10 to the minus 18 meters, which is very small, right? Smaller than the size of the nucleus. You should not imagine that it looks like this, obviously, but it's pretty cool that nevertheless we can measure these very small displacements of our lattice. So in some sense, this cat is quite massive. In other sense, it is very small. Okay. Another thing that I want to point out also, that you should definitely not imagine the atoms as looking like this, right? Because this is only the motion in a single mode. There are 10 to the 17 other modes in this system, many of them at much lower frequencies and thermally occupied. So the atoms are like actually doing all kinds of crazy stuff, right? But for this particular mode, it is in this nice quantum superposition. Okay, so this was some work that just came out last year. It was done by 2 of my PhD students and our postdoc, Matteo. Yeah.
What extent would any crystal defect or imperfection affect? Because you're actually you have a small separation, but if I'm understanding this right, you still measure it because you're looking at zillions of atoms that contribute.
Yeah, we're looking at the collective motion.
If we're not all sitting at the right place or doing the right thing, then you
For sure.
wash it up.
Yeah, I mean, we think, you can ask the question, like, what limits, say, our phonon T1s and T2s, right? What makes it this not a perfect coherent motion that goes on forever? And it's probably because of things like dislocations and defects and surface roughness and things like that. So speaking of that, we're looking into this. Of course, this is a question that we're very interested in. So one that we've been looking at is actually investigating the properties of these modes over many modes. So this is a Fabry-Perot cavity, right? There's a mode every free spectral range, just like in an optical Fabry-Perot cavity. So what we did was actually we replaced our qubit with just a vector network analyzer. We just hooked it up to an antenna that also couples to this acoustic system, and we're looking at the reflection of this circuit. And what it looks like is this. It's a little hard to tell what's going on, right? But usually, without the mechanical resonator here, this thing would just reflect back. So your S11 would just be 1 or 0 here in this log scale. And then what we see on top of that is actually this very dense forest of lines. So maybe let me zoom in a little bit, and then you can actually see what's going on here. You see these very narrow lines. Okay, this is what you expect for a high finesse Fabry-Perot cavity. What we see is like every 10 megahertz or so, we have a sort of 1 kilohertz line width mode. And so there are many of them. And so one interesting thing we're looking at is how the line width varies across these different modes. And we actually see that even though they live in the same physical resonator, their line width can vary by a factor of 5 or 10 from one mode to the other. So that's a bit mysterious. Maybe it tells us something about what leads to the losses. But it's also interesting to now, this is something I mentioned at the beginning, right? That this very compact object has many modes, and that's an interesting resource, right, if you want to do some sort of quantum operations. So very quickly, so this was some measurements started by my PhD student, Ariana. And very quickly, I'm not going to go into this in detail, but we started looking at some multimode operations, looking at operations between mechanical modes, so not between the qubit and mechanical modes, but let's say 2 or 3 different mechanical modes in this comb of modes that we see. Right, so for example, we've been able to actually implement a sort of beam splitter interaction between these 2 modes, so have 2 mechanical modes directly exchange energy with each other. And we actually do that by parametrically driving the nonlinearity of our qubit. Okay, I'm not going to say more about that. If you're interested, I can explain more how that works. And of course, if you can do that, you can also generate entanglement between 2 mechanical modes. Okay, so that's about to come out, I think, sometime next week in Nature Physics. Okay, so that's what I wanted to say about our electromechanics in the remaining 10 minutes or so. Let me quickly go through how we are also probing our mechanical modes with optical infrared light. And the idea here is simply that we're going to take our Fabry-Perot cavity for sound, we're going to put it in a Fabry-Perot cavity for light. Okay, because why not? So this is our physical system, right? So we have, again, now we're taking an even larger, more macroscopic piece of quartz crystal. So now this is sort of a 5 millimeter long piece of crystal instead of the wafer that we used before, which is about 500 microns in thickness. And then we're putting those between some mirrors. We have some fibers that couple in the light. We put this whole thing in a pretty compact bracket and it's all fiber coupled because we're going to put this in a dilution refrigerator. Okay, so that's actually a non-trivial task because dilution refrigerators are not optics tables and they vibrate a lot. And so we, just for fun, I'm showing you this video of a suspension system that we built to vibration isolate this free space optics system while also keeping it thermalized to our fridge. Okay, so that seems to work pretty well, actually. Now let me quickly describe how this thing works. So again, the idea is here, right? You have your mechanical crystal, you have these standing waves, that are your mechanical modes. You have your optical cavity, you have standing waves of your optics, of your laser light. And inside, right, you have many different mechanical modes and many different optical modes separated by their respective free spectral ranges. And there is a process called Brillouin scattering, which I think some of you are also very familiar with, where essentially this mechanical mode acts as a grating because right, these acoustic waves essentially leads to density modulations of your crystal, which leads to indexed modulations, so it sort of acts as a grating for light. And so light can scatter, in particular, can, for example, scatter from one optical mode to the neighboring optical modes through this mechanical mode. And this happens if you satisfy a few conditions. You have to satisfy energy conservation, as usual. So the separation between these two optical modes has to equal the frequency of the mechanical modes. You have to satisfy momentum conservation, as it turns out, because it's sort of an extended system. If you put these things together, you get that this happens only for a certain narrow band of frequencies of your mechanical modes. And this depends on your material and wavelength of light. So for example, for quartz at 1550 nanometer light, this is about 12.6 gigahertz. So also a pretty, convenient frequency range. As I mentioned before, all of our other experiments also done in the gigahertz frequency regime. And finally, I'm writing down now a quantum description of a sort of optomechanical interaction Hamiltonian. And this is exactly the process I just described, right? You can scatter between these three modes. You can annihilate a phonon, for example, and scatter a photon from the mode AJ to the mode AJ plus 1, let's say. Okay, sort of a standard optomechanical interaction, but now there's sort of just two different optical modes involved, but it's still this sort of three-wave mixing situation. And you can also write down the interaction strength of this thing, which looks complicated, but really all it is the overlap integral of these three standing waves, okay? And it depends on things like the photoelastic constant, of course, and things like that. Okay, so once we have this, what we can do is sort of some standard optomechanics experiments. In particular, what we wanted to know is, can we measure this even larger mass crystal, for example, in the quantum ground state, which it should be in because it's a gigahertz frequency mode, and we put it in a dilution refrigerator, right? So to do that, we're going to use a very well-known technique in optomechanics, which is sideband asymmetry thermometry. And the idea is quite simply the following. Right, so this scattering process, right, depending on whether let's say you put in some laser light at the lower frequency optical mode, right, and it undergoes sort of anti-Stokes scattering process to the higher frequency optical mode, right? So that involves annihilating a phonon, and so that process is proportional to sort of the thermal occupation of your phonon mode if you don't drive it or anything like that. And then there's the opposite process, right, which is a Stokes process where you actually create a phonon, and then that's proportional to your thermal occupation plus 1, as it turns out. And so we're going to try and look at these two scattering processes, right, by simply putting in a laser and locking it to one or the other mode, the lower or higher frequency optical mode, and then looking at the scatter spectrum through a sort of heterodyne detection scheme, and then look at the scattered spectrum that was mediated by the thermal phonons in our system. Okay, so if we do this, this is what we see. So first, as a sanity check, we cooled our fridge down to just 4 Kelvin, and we see this a slight difference between these two. So the color schemes correspond to these two situations, right? And we find there's about like 6 or so phonons in our systems, which is exactly what you would expect for a 12 gigahertz mode at 4 Kelvin. Then we cooled our fridge down all the way to base temperature, which for us, because we were like shining a laser in there, was only 200 millikelvin, not the usual 10 millikelvin. And now you see a significant difference between your Stokes and anti-Stokes scattering processes, right? This blue thing is much larger than the red thing. And if you just sort of look at the ratio of these, you can calculate thermal occupation. We find that indeed this ends up being less than half a phonon of thermal occupation. It's actually a bit higher than what you would expect from 200 millikelvin, probably because our system is not perfectly thermalized to our fridge. Okay? So now to put this in context, I stole this picture from a recent publication from LIGO, where they were cooling their mirrors down to close to the ground state. So these are all like experiments where people actively cool mechanical resonators to or close to the ground state. So we're kind of cheating because we just put them in a fridge. But okay, and nevertheless, I put the 2 points here from the 2 experiments I talked about. So this one here is colder. It's our smaller mechanical resonator. This one is actually even a bit more massive. It's about I think 100 micrograms or a few hundred micrograms, and it's sort of up here. So still in the quantum ground stage. Okay. All right. So sort of if you look at these 2 parts that I've talked about, right? I've talked about how we can couple our mechanical modes to circuits. We can couple them to light. One obvious thing that you can imagine is putting them together. And this is what we're actually one of the projects in our lab, which is to actually build a transducer between our microwave circuit, our superconducting qubit, and infrared light. And of course, the thing you want to do there, right, is imagine taking the quantum information that you process in your circuit. Now it's at microwave frequencies, right? You can't just take it out into room temperature. You have to convert it into much higher frequency, for example, infrared light, if you want to send it, let's say, over long distances through a fiber or something like that. And this is an ongoing sort of goal in the optomechanics, electromechanics community for a long time, and many people are doing this, and we're going to try also to do this with our acoustic resonators. So that's sort of ongoing. And then let me come back to this slide here that I showed at the very beginning. So that's one of the things that we're looking at. So in the theme of sort of interfacing different quantum systems with our mechanical oscillators, we also recently started a project coupling them to color sensors. So it turns out that if you strain a crystal, the stuff that's in it responds. And so you can couple, for example, color sensors in diamond to acoustic waves in diamond. So very good acoustic material also. So that's something we started looking at. Now, in these other 2 directions, now I showed you, for example, these quantum gates between multiple acoustic modes. And now we have sort of the basic operations for like controlling their quantum states, measuring their quantum states. And now we're looking into, for example, making more complex operations, performing a full quantum gate set between different acoustic modes on single modes, multiple modes, performing, for example, C-phase gates between these acoustic qubits, essentially. We actually have another project making a mechanical qubit. I can tell you more about that later, but what it means is basically we're trying to make the nonlinearity of our mechanical resonator stronger than its decoherence. And it turns out I think we were pretty much there just by giving it some of the nonlinearity of the qubit. Okay, so I won't go into details, but that's a fun thing that we're doing. We actually also started exploring this direction here. We talked to some people who were interested in detecting high-frequency gravitational waves. so up to gigahertz regimes, so making a mini LIGO essentially. So it turns out that our system is a mechanical object. When a gravitational wave passes by, it drives it. So in principle, it responds to gravitational waves, and we can measure it very sensitively. We can measure a single phonon, like even less than that in our system. So we've been thinking about, like, can we do something interesting with that? Okay. So, but that's that about summarizes what we are up to. We've been up to, and where we're going. So here's just a picture of all the people who've been working on this. This was taken last summer at sort of a local maximum in the number of people in my group, so including master students and summer students. You saw many of them already as I went through the slides. And then we're also collaborating with many wonderful people who grow materials, theorists who tell us what to do. So thank you very much for your attention. I'm happy for questions.
Well, thank you very much for that great talk. So I'm sure there are questions around in the audience. So who wants to start? I see a first question there, and okay, the guys in front, watch out.
Nice.
Well, first of all, thank you very much for the talk. It was very nice. I have a question about the last thing you mentioned about the electromechanical resonators, where you have like this oscillation between two phonon modes.
Yeah. Okay. Right. I didn't go into that in much detail, so I can happy to talk about it more. This one.
So you said that this corresponds to like a beam splitter interaction, but correct me if I'm wrong, but would this also be a strong coupling between two phonon modes?
Yeah, right. So you would only see this if the beam splitter, right? So the Hamiltonian, which I didn't write down, right, is, you know, A dagger B, right, where A and B are just your two harmonic oscillator modes, and the prefactor to that has to be larger than both of their decoherence rates in order for you to see this coherent oscillation. So yes, it is a beam splitter interaction in the strong coupling regime, if you like. Yeah.
But here, so you will have like two acoustic modes that they're exchanging energy with each other.
Exactly.
And you just have they're strongly coupled because the coherence rates are so low because, I mean, you're at like a very low temperature and then you have like very good cavities, let's say, or?
Yeah, well, so let's say, I think I don't remember the exact numbers, but the properties, the basic like phonon properties are comparable to the ones that I'm showing here. So like, you know, tens, 100 microseconds or so, right? And so indeed, right, it's important that they are so long-lived because as you see here, right, the coupling strength there is only about 16 kilohertz, so sort of another order of magnitude lower actually than our native qubit mechanical coupling strength, because again, this is sort of a mediated interaction through the qubit, so it gets sort of order of magnitude hit. But nevertheless, our phonons are coherent enough that we can still afford to get that, to take that hit, basically. Yeah.
Thank you.
Also, thank you very much from my side. I have a question regarding the temperature. So, is it always the colder the better? Because then you have less thermal phonons. But is there also maybe a sweet spot in terms of coherence times, or is there something else to consider? Or is it really, if you can go to like a microkelvin, this will be perfect? What's your wish temperature?
Okay. So I mean, so far we've been we actually been measuring the temperature of the phonons very carefully for this gravitational wave detection experiment. Basically, you know, you can, if you see that your phonons aren't excited at all, that puts some bound on whether or not there are gravitational waves around them, very briefly. But so we see that they are very cold. Actually, in these circuit QAD systems, the thermal occupation is like 0.1% or something like that. So for everything we've done so far, that's good. And for this, you know, gravitational wave sensing experiment, that's actually the number that we care about. So that's good. We don't. I think we haven't looked too much into how much the phonon parameters or the quality factors, let's say, change with temperature. I think we have seen that it doesn't change too much if you go up to like 100 millikelvin or so. If you go up to 4 Kelvin, they are worse because you have phonon scattering, things like that. So for now, I would say, yeah, the colder the better. Yeah.
Okay, thank you very much.
Okay, more questions? Yes, there's
one. Dispersive experiment.
Yeah.
In the last figure where you had like 4 phonons, can you explain the distribution you have in the other levels? Like you have
this
also
one? Is this what you mean?
the topmost one, you have also certain population, certain probability of having 2 phonon, 1 phonon. Can you explain?
Yeah. So that's just because, right, there's a whole protocol to measuring this, right? First, we do this iterative process of putting phonons into our mechanical resonator through the qubit, right? And that takes some time. And then doing this measurement also takes some time, right? And so during that time, our phonons are pretty long-lived, but they still have some decoherence or some decay rate, right? So you put 3 phonons in there, and there's a finite probability that 1 left, and you end up with 2, right? Or 1 or 0. So it's just that the energy decay essentially during this whole protocol that we see. So that's why when you get around to measuring it, right, there's sort of a distribution of photon numbers that are left to your resonator.
But then again, you shuffle them around because it's a linear system. When you send a photon, you can act on all the levels.
Okay, so ideally, this dispersive interaction, right? If you look at it, it doesn't excite or de-excite your phonon mode, right? It's coupled to a dagger A, right? So the phonon number commutes with the Hamiltonian. But in the ideal dispersive regime, but again, we have imperfections in our measurement. So probably also when we do the measurement, it does perturb the phonon number a bit, might even excite it a little bit. But those come in sort of, those are all things that contribute exactly to this distribution. Yeah.
Okay, there are more questions.
So could you give a perspective? I mean, you sketched lots of exciting things that you're doing and you want to do. Could you kind of give us the dirt on how difficult these things are and what the limitations will be?
Sure.
You talked a little bit about the material things, but...
Okay, so let me go back to this slide here, maybe. Right. Okay, so I would say, on the sort of quantum processing and sensing side, I think the sort of initial proof of principle experiments, right? I think we're doing them. We can do them. In the end, right? But I think we're already sort of running up to the limitations of our basic hardware parameters, right? So I didn't mention this explicitly, but I sort of briefly showed it, right, with the spectroscopy of the many phonon modes. We are also spending a lot of effort into improving the basic hardware parameters, right? So, for example, the phonon lifetime, and actually in particular the qubit coherence, which if you saw was much worse than the phonon coherence, and much worse than state-of-the-art superconducting qubits. So actually, if we just make a qubit, it's much better than before we slap our acoustic resonator on there. So it has something to do with the fact that we couple it to this material.
Is the quality of your superconducting qubits basically the state of the art that you're...
Before we couple it to the phonons, it's not like the best. We're still using sort of not the most state-of-the-art materials and things like that because it's just easier to make our current to use our current fab process. But it's not. But the thing is, it's not limited by the intrinsic sort of fabrication of the qubits, right? It's limited by the fact that it's coupled to these phonons or to this mechanical resonator, and we think we understand why that's the case very briefly because it couples to other phonons that not other than the coherent phonon that we want to couple to, and that just radiates energy. So we're actually trying to redesign the system to deal with that issue. I think a lot of our experiments right now are limited by the qubit coherence, actually, on this circuit QAD side, which is what we're using for the information processing, the sensing stuff. Okay, the transduction, of course, is very, very challenging. It's a very complex system. So, and there are many other alternative systems that work very well. So I think for our system to perform at like the state-of-the-art level, that's going to be that's very challenging. But okay, I think we have a way of doing it, right? It's a matter of putting all the components together, and probably we will find some surprises along the way. But yeah, that's where we're going.
And the last bit is
this one,
particularly interesting to us.
Right.
Can you say something about the development in that direction also in other groups? So how far is one in terms of coupling individual quantum emitters to mechanical oscillators?
Right. So we are just getting started again. Also, other people have been working on this for quite some time. So let's say maybe people have coupled, I think, nitrogen vacancy centers to bulk acoustic wave resonators and silicon vacancies. So this is the reference to surface acoustic waves. But it's not in the strong coupling regime. Let's say they can see that you can use the acoustic waves to drive Rabi oscillations of your spin qubit, but like a classical drive, right? So I think the next milestone would be seeing strong coupling, and that's what we're trying to get to in our system, because our phonons are much more coherent than, let's say, in a surface acoustic wave resonator.
Yeah. Thank you.
Mm-hmm.
Very good. Are there more questions from the audience?
Okay.
Maybe we first take Birgit, and then we can look at Zoom.
You went very interesting work, as always.
Thanks.
You said something in the beginning about this picture, that the acoustic wavelength is much smaller, and that's why you can integrate it on a much smaller footprint. Compared to electronics?
Compared to, let's say, if you make a microwave resonator at the same frequency, right? It would have to be, much larger.
And what's the order of magnitude of reduction?
So the speed of sound in Sapphire, I think it's like 4 orders of magnitude or so. Yeah, is the difference. Yeah.
Thank you.
Mm-hmm.
Okay, very good. So now I can't read from this distance. Maybe you can read one of the questions, if that's possible.
Wait, here, I can... okay. Okay, so it says in your slide 22, the entangled mechanical mode using the acoustic beam splitter is an EPR or 2-mode squeeze state. No, actually, okay, I'll just stand here and answer it. It is actually it's entangled in the Fox state basis, right? So the state, okay, no, sorry, now I have to come back here. Okay, let me see here. I think I wrote down what the state is, right? Yeah, so this is this is not a 2-mode squeezed state, right? It's a superposition of the phonon in one mode or the phonon in the other mode. I hope that answers the question. Okay, should I read the second one? Okay, second question: how does time react in general in this environment you are working in? Okay.
That's a philosophical question.
Not sure. Not sure how to answer that. Yeah.
Anyway, so is there some urgent further question here in the audience? I don't see any. We had many, and anyway, as usual, there is food outside, which also gives you the opportunity to have further discussions with the speaker. And now we thank you again.
Thank you.